Welcome to the third module in Introduction to Robotics. Last module we talked about a variety of sensors that are inspired or are being used in industry and consumer electronics, and the key takeaway message was really that there are no robotic sensors per se. Most of the sensors we are using in robotics are actually derived from consumer applications such as the smartphone, gaming, or the car industry. We've been talking about sensor performance using the example of a laser scanner that comes with a little data sheet, and important quantities are the range, the dynamic range, resolution, linearity, bandwidth, cross-sensitivity, accuracy, and precision. And to best understand precision versus accuracy, I provided you with this graphical representation where you can see things that are very precise and accurate, or not precise and accurate at all, or very precise or very accurate but not precise. We've also been talking about an equation to estimate accuracy from true measurements and true values and measurements, M and V. We haven't given you an equation for precision because it involves the concept of variance, which we will treat only later in this course. In the lab, we've been looking at data sheets from real robots, and what I've done there is I sorted them by the abstraction level. So the interface for the universal robot is in URScript. It's their own language. You can program the robot in Java. The Robotics motor is programmed by setting a bunch of registers, so it's very low level already. And a sensor for distance measurements is really interfaced at the level of electronics. Now in VBots, all of these are well abstracted in Python, but do maintain the properties that they have in real life. Alright, so this module is about reactive behaviors in state machines. And for this we will start with a video from 1950s.
Now meet Dr. Greywalter of Bristol. Why the torch? Well, here's the reason. It's Toby, a mechanical tortoise with an electronic brain which functions like the human mind. Toby's head, or rather magic eye, is a photoelectric cell constantly revolving until it picks up the strongest source of light, to which it is then attracted. In this case, an ordinary electric torch guides the mechanical tortoise in any direction its inventor chooses. It can also negotiate obstacles. When it hits an object, the pressure on the shell causes a short circuit of the photoelectric cell mechanism, and the tortoise moves at random until it is free of the obstacle. Source of light placed in position, Toby is attracted to the lamp in the same way as a moth is attracted by light. Now the front wheel of the tricycle undercarriage, which is coupled to the photoelectric cell motor, is turning on its axle while the two back wheels remain static, and the tortoise attempts to get still closer to the light. The syringe is being used to inflate the tires. And with its shell removed, the inner workings of the complicated mechanism of Dr. Walter's brainchild and the immediate effect of light on the magic eye can be seen. Toby is probably getting tired and hungry by now, for light to Toby is like food to any ordinary animal, and that light in his hutch never fails to bring him home, without a torch too.
So this is a very simple device using analog electronics, and it has been built by a neurophysiologist. So this researcher wasn't a roboticist, but he was interested in understanding how the brain works and making hypotheses thereon. This work is still relevant for today's most successful robots like the Roomba, which use very similar techniques to navigate in the environment and here find the charging station. So the charging station in this case also has lights to attract the robot. It's a little more sophisticated. They are using what they call a green buoy and a red buoy, and they achieve this by using an infrared light source that encodes different signals using really a standard TV infrared remote control. So let's say this is volume up and this is volume down. And so this Roomba has multiple infrared receivers or remote control receivers, like the ones that are in your TV. And when it sees the green buoy on the left and the red buoy on the right, it knows it can stop turning and drive straight to approach the charging station, which is then also communicating via a short-range force field signal, so it knows it has arrived. Valentino Braitenberg came in a little later, and he essentially picked up on where Sir Walter Gray has left. He was a professor of cybernetics, also a neuroautonomist, and he wrote a book called Vehicles, Experiments in Synthetic Psychology, where he came up with a couple of very simple vehicles, as he called them, that use very basic sensors and actuators and an increasingly complex network to wire them together. So the first vehicle he proposed was a vehicle that directly couples light sensing to the motor. So the brighter the light shines, the faster the motor turns. And he also understood that the robot is a physical system that is subject to friction, for example, which then can introduce nonlinear behavior. So in this case, the device wouldn't start until the light would turn bright enough so that the motor turns fast enough, strong enough to overcome friction. He then came up with one level up using 2 sensors and 2 motors. And when you think about this a little, and you put a light source here right in the middle, you could see that this light shines brighter than, or the light shines brighter here on this sensor than there because it's a little closer to the light source. So this motor will turn faster than that one, and the vehicle will turn away from the light source, just like so. Now, when we cross the wires, then this one will be brighter than that one. So this left motor will turn faster, and the robot will turn toward the light. So you might wonder what happens when you drive very straight to the light. How can it avoid when both of the light sensors have the same brightness? Now, what happens in practical systems and in the brain, there is a lot of noise. So there will be a moment where one of those sensors receives a brighter light than the other. There will be a turn to the left or to the right, which will then get amplified, and the robot will always turn away from the light. So the symmetry breaking, which might happen in a mathematical system or in a computer program, doesn't happen in the physical system because of noise. So there's an example in nature which is called phototaxis, and this is an algae which would like to be closer to the light to increase its photosynthesis. And so this simple cell has little flagellas on it that rattle and allow the bacteria to swim. And what it can do is it can change the behavior of these flagellas so that the flagellas work against the direction of motion, or actually break it. So in this case, it would be enough to, if they would just be turned off by the light, then this cell would actually not continue toward the light. In this case, they move slightly backward too, so there is actually a light avoidance behavior. And now what happens a little later, only the flagella that are directly exposed to the light exhibit this behavior, that braking or backward behavior. And so the ones to the left are stronger, turning the cell toward the light. Now, once they are both turned toward the light, again, the backward flagella will be stronger than the frontward ones, and then it will move toward the light. So you see, this kind of behavior happens everywhere. It happens on the smallest cellular scale. It happens in industrial consumer robots. And it probably also is similar to how the pathways in the brain wire sensing and actuation together. You can also use this to avoid collisions, and you've seen it in the video. The shell has been connected to a sensor that, when triggered, let the robot move in a random motion. You can do better than this with more directed sensors, like on the ePark, and we talked about the proximity sensing in the last module. Now, if you have something like this, you could actually directly affect the wheel speed as the distance sensor gets higher. That means if you are approaching the obstacle, this distance sensor gets higher. I can directly subtract it from the motor speeds, which makes the robot slow down. And then same thing, the symmetry might be broken very quickly due to noise. So that means one of the motors will turn faster than the other and the robot will turn. So this is something you can very easily check out on Robots. There's a specific video just for that. Let's move on to compound behaviors. Now we might be interested in having not just avoidance, but light following, like you saw on the tortoise. And what we can do in a computer is we can just superimpose the different sensor values using a weighted sum. For that, I took a Braitenberg vehicle and I added two other sensors, which are the light sensors. And now I can use the light sensors in a crossed way, so the robot will approach the light source, and I can use the distance sensors to avoid the obstacle. Also, this is something you can try out yourself in Robots and watch another video in the module. All right, some observations here. In order to get these things done, you do not need any memory or any computation. This can be literally hardwired. So you can order these sensors from DigiKey, you order motors from DigiKey, you have a battery, and you connect them so that the sensor output directly triggers the motors, for example, using a transistor. When you look at the equations in the computer, the weighted sum that I mentioned earlier, this really looks like a neural network. So I just turned this Braitenberg vehicle around, and so what we see is we have a 4x1 input, which are the two sensor readings for each sensor modality, and we have a 2x1 output, which value are directly computed by a weighted sum from the input. Now you can think, of course, to make this arbitrarily complex here and create very interesting sensor-based behaviors that do not need memory and very basic computation. Now, there are some situations that you cannot solve without memory, such as driving out of a U obstacle where the robot gets stuck here because it wants to drive to the light, then it wants to avoid the obstacle. Once it has turned around, it says, oh, wait a minute, I actually want to turn toward the light. And so you have it stuck unless you memorize this and say, hey, no, I am stuck. I have to work on getting out of here before I can move on. Also, it is very difficult to fine-tune the sensors, the computing, the wiring, and the environment. And I say this because in Robots you can also play with the light source intensity, which completely changes the behavior that you just accomplished by tuning the parameters. So you will see environment, device physics, where the sensors are located, for example, and the program are very tightly entwined, as we showed you before. All right, so if you have memory available, you can do something more sophisticated. You could say, I want to have multiple reactive behaviors like light following or obstacle avoidance that I switch based on external events. So, for example, I could follow the light until I detect an obstacle, then I want to avoid this, and then I can go back to light following. I can even do something smarter. If I avoid the obstacle and thereby turn away from the light, so the light decreases, I could go into a new mode called wall following, where I drive along the wall until the light increases again. That means I have been turned around the obstacle and approached the light source again, where I then jump off the obstacle by avoiding it and drive toward the light until I'm under the light and stop. So the formal definition for such a state machine is you want to have a finite set of states. I want to have an initial state as 0, and I need something that is called an input alphabet. The input alphabet are the events that trigger different state transitions. And so you see here with every state transition I have an event associated, which is known as the alphabet. Then I have a state transition function delta, which is all the states times all the different input alphabets, mapping again to any of the states that I can reach, and a set of final states like the stop in this case. So here I worked that out, and that's why I like Python a lot to explain things and teach, because Python syntax is very close to mathematical syntax. Now I don't have the sigma symbol, but you can see how this maps directly to a Python set. Very convenient. So I have the finite set of states here, which are those 4. I have the in alphabet 1, 2, 3, 4, 5 state events, and I have the final state. Now I have the state transition function where I have rows, 4 rows for each state, and I have 5 columns for the different events. And when something happens, like I'm in follow light and I get the under the light event, I know that the next state is stop. If I'm in follow light and I receive an obstacle detected event, I'm in avoid obstacle. Now these state machines have their limitations. Sometimes you might run different things on a computer. For example, if you have something like an event light decreases or light increases, I probably would need to monitor the light over a couple of time steps. And in this case, I would write a program that computes the running average, filters outliers and drops them. And then as soon as I really find that the light increases or decreases, I can trigger an event. And in order to do this, in robotics, you usually use hierarchical finite state machines, which are different programs, each running their own state machines, and are coupled with message passing. And in this case, I have the state machine that we just talked about, which is the light follower, which now has 2 new events, LD and LI, which are light decreases and light increases, which are emitted from this other process. And in practice, I would really run 2 processes, 2 threads on my computer, 2 Python programs, 2 C++ programs, whatever, and I use message passing to connect them. Finite state machines also have other limitations. They're very brittle. When you program them, a lot of things can go wrong. You might end up in unexpected states very quickly, something that you didn't take into account, or you will find that the states you have are simply not sufficient to implement a desired behavior and have to add additional states, which then becomes difficult. Now, if you have, let's say, 4 states, as you've seen before, you have up to 16 state transitions. So it's really n by n, because you might find, I can also go from follow wall directly to follow light, or I could go from obstacle directly to stop because there was an obstacle right under the light source, and so on. And as you find that out, as you experiment with your robot, you will have to add states and you have to add transitions. And this is all very cumbersome to maintain. So there's something better we will learn in this course, which is called behavior trees. It comes from the gaming industry. Here you see behavior trees in the Unreal Engine. We will also talk in other courses in this sequence about the robot operating system, which is a nifty way and a set of tools to implement multi-process robot programs. But this goes too far in this course, where we will stick with a single Python script in our Webots simulation. This week, you should right away go on and solve the quiz in Module 3. I want you to implement a basic state machine in Webots and then perform your first peer review assessing your peers.